Section 11.4.9, we want to assume that the populations are normally distributed. We're going to test the hypothesis that population standard deviation 1 is not equal to population standard deviation number 2 at the alpha equals 0.05 level of significance. So here's sample 1 and sample 2. The sample size n is 21 here. For sample 2, it's also 21. The sample standard deviation is 4.1 for sample 1, and the standard deviation for sample 2 is 4.2. So the first thing we need to do is we need to identify the null in the alternative hypothesis. So we already know what the alternative hypothesis is because that's what we're testing. It's the not equals. So we have the population standard deviation 1 is not equal to population standard deviation number 2. So that means we have population 1 standard deviation is going to equal population standard deviation 2 for the null hypothesis. Now for step 2, since this is not equals, we know that this is going to be a two-tailed test. And then number 3, we now need to identify what is alpha. We know that alpha is going to be equal to 0.05. Okay, now what we need to do is we need to take a look at the test statistic. Okay, so let's take a look at the test statistic here. All right, so if the following, this is the population variance squared is equal to the population variance 2 squared is equal to the variance of sample variance squared of population 1 and a sample variance of population 2 are sample variances from independent simple random samples of size n1 and n2 respectively, drawn from normal populations. Then a test statistic defined below here follows the F distribution with n subscript 1 minus 1 degrees of freedom in the numerator and n subscript 2 minus 1 degrees of freedom in a denominator. Okay, so the first thing we need to do is we need to find the test statistic. So from our problem, okay, we should see that the following. We know that sample 1 has a standard deviation of 4.1, and then sample 2 has a standard deviation of 4.2. So now let's go ahead and then enter that in for our problem. So we know that standard deviation 1 is going to be 4.1, and then we got to square it, and then we're going to divide that by 4.2, and then we're going to square that. Okay, so let's go ahead and put that in our calculator. Okay, so we have 4.1 squared divided by 4.2 squared. So let's go ahead and take this value. And now what we're going to do is we're going to round that to 2 decimal places. So if we round it to 2 decimal places, then we get a test statistic of 0.95. Okay, now the next step is we need to find our critical values. Okay, so our critical values, but we need some information. Okay, first thing is that we know that alpha is equal to 0.05. And then we need to take alpha and we need to divide it by 2 because this is a two-tailed test. So 0.05 divided by 2 is going to give us 0.025. Also, we want to be able to find out what is 1 minus alpha divided by 2. So 1 minus 0.025 is going to equal 0.975. Okay, what else do we need to know? Well, we need to know the degrees of freedom in the numerator. So we know that n1, okay, is equal to 21. So that means we're going to take 21 minus 1, which is going to equal 20. We also know that n2 is going to equal 21. So 21 minus 1 is also going to give us 20. Okay, so now we need to find our F distribution critical values. Okay, so let's take a look here. Now, if we take a look at the critical values formula, okay, here's our first one. Okay, so the first one here, recall that this becomes F, which is 1 minus alpha divided by 2, which is 0.975, with the degrees of freedom in the numerator to be 20. And this is also 20. Okay, and that's going to equal 1 over, we have F, now that's alpha divided by 2, which becomes 0.025, and then we flip the degrees of numerator and the degrees of freedom in the numerator and denominator, so it's still going to be 20 and then 20. Okay, so let's use our F distribution table. We know that we're looking for 0.025, so we're making sure that we're using 0.025. Okay, and we know that we have degrees of freedom in the numerator is 20 and the denominator is also 20. So let's go ahead and find that critical value. So we know that the degrees of freedom in the numerator is 20. The degrees of freedom in the denominator is 20. So let's go ahead and find that critical value. And so we end up getting 2.46. So this becomes 1 over 2.46. So 1 divided by 2.46 gives us the following here. So we're going to round this number to 2 decimal places. So rounding that to 2 decimal places gives us the following, 0.41. Okay, so now we want to be able to find the next one, which is F, and alpha divided by 2 we know is 0.025, so that's 0.025. We know degrees of freedom in the numerator is going to be 20. Degrees of freedom in the denominator is also going to be 20. So let's find that value. Okay, so we know that it's going to give us the same value. So we can see here that when we go ahead and go 20 here, and then go 20 there, it's still going to give us the same critical value. So therefore, this critical value is going to be 2.46. Okay, so now what we want to do is we want to be able to now draw our picture so we can determine where is the critical region. So here is our graph. Okay, and then we're going to go ahead and draw our critical values. So our critical values are located at 0.41 and 2.46. And then marking in red is our critical region. Okay, so the red is our critical region. Okay, now let's go ahead and form our conclusion, okay, for step number 7. All right, now in order to do that, in order to form our conclusion, what we need to do is we need to come back and take a look at the test statistic. Okay, so what is the test statistic? Well, the test statistic that we found here is 0.95, right? So where does 0.95 fall on our graph? Well, 0.95 is in the middle. So here is where the test statistic is. Okay, and that test statistic is F subscript 0, which is equal to 0.95. So we can see here that it does not fall within that critical region. Okay, so what that means here in step 7 is the following. Okay, the critical region has the form of the test statistic it has to be either less than 0.41, so it has to be within that region, or it has to be greater than. So we notice that it's neither, right? So we reject the null hypothesis when the test statistic is in the critical region and it's not in the critical region. Otherwise, we do not reject the null hypothesis. So therefore, since it's not in the critical region, then we do not reject the null hypothesis. So we do not reject the null because the test statistic is not in the critical region.